Hey everyone, so welcome back to our next part into the deep dive of the Google file system. So far we've understood why Google file system was needed and how it is structured, right? In this session we'll try to explore how data actually flows through the system, what is the read and write flow paths, what is consistency mechanisms, what are recovery, and how checksum works to maintain the data integrity, right? And towards the end we'll get a sneak peek into the master node that is the brain of the Google file system. So yeah, let's dive in. All right, data replication, right? The first question is, why do we need to replicate data, right? Imagine a scenario where library is having only one copy of the book, and let's say if that book is damaged or lost, the knowledge that that book contains is forever lost, right? To solve this, library would maintain multiple copies of the same book across different shelves, right? That's exactly what GFS does as well. Right? Each chunk of data is stored across multiple chunk servers, right? This helps us maintain, first of all, fault tolerance. That is, if one server fails, we still have data somewhere else, right? Second is high availability. That is, readers can always get data from a copy or one of the servers, right? And third is load balancing. Instead of sending all requests to a single server, we are now able to distribute requests across multiple servers. So replication is the safety net that ensures GFS never loses its data because of single point of failure. Now let's see how GFS handles the reading data, right? Client would ask the master server where a particular chunk lives, right? Or where this particular chunk is stored, right? Master server would check its metadata and would respond with the list of chunk servers that has that particular chunk. You can imagine like master returning response saying, hey, this particular chunk is present at chunk server A, chunk server C, and chunk server F, right? Now the client can directly go to any one of the return chunk servers and fetch the data, right? Let's imagine that if one of the chunk server is unavailable or is not having that particular data, or the data is corrupted, any failure scenario, right? The client can directly fetch data from another chunk server that was returned to it by the master server, right? That's why multiple locations or multiple chunk servers are helpful here. There are a couple of optimizations that are done on top of this, right? Client, first of all, caches the list of chunk servers that was returned by master, that is called metadata caching, so that it doesn't have, let's say if a user is requesting for same chunk again, it doesn't have to go back to the master and re-ask for the list of chunk servers, right? Second optimization is, client also tries to fetch chunk servers data for multiple chunks in a single go, or we call it bulk request, right? Like the client can ask, hey, master, can you return the servers which are having chunk 1, chunk 2, and chunk 3, right? So reading in GFS is like you asking head librarian, hey, where is this particular book is present, and head librarian responds with you the locations of list of locations where that particular book is present, and you can fetch the book from the location that is easiest to access to you for you. So reading was pretty simple, right? Let's now try to understand what is the write flow path, right? And this is where things get interesting. Imagine multiple clients are trying to write to the same chunk at the same time, right? And if one of the client writes for the, and another client writes system design, right? We don't want our system to be in a state where one of the chunk server is having system design for the, and another chunk is having for the system design. This is basically a data inconsistency, and this is not acceptable, right? So let's try to understand how Google file system solves this particular problem. Whenever a particular client wants to write data, Client would first check with master on what is which server is having lease to a particular chunk, right? Lease is basically the authority to act as the primary for that particular chunk, right? The master server would then check which particular chunk server to give the primary and what would be the secondary for that particular chunk, right? Suppose chunk server 2 is primary for this particular chunk, and chunk server 1 and 4 are the secondaries, right? The client would send data to all of these primary and replica servers, right, and would wait for the acknowledgement from each of those servers. What these particular chunk servers would do, they would basically write this data into memory. Please note here, they will write into memory and not into the disk, right? Once client gets acknowledgement from all of the servers, client would ask primary to commit the data, right? What primary would do, primary would write the data that is present in memory into the disk and would request all the secondaries of that particular chunk to write or basically to commit data in the same order that primary is having. This way, every replica ends up having the same exact version of that particular chunk, right? Now let's understand atomic record appends. When multiple clients append data to the same file, GFS ensures that client's data is written completely and cleanly, that is without overlaps or corruption, right? It's like librarian letting students add notes to the page one by one, such that each note stays intact even if multiple students are So next is the consistency model. Now, is our system, that is Google file system, always consistent? Not exactly, right? Sometimes the master believes that this particular chunk is having 3 replicas, while one of the replica might be corrupted or missing, right? That's an inconsistency state because we only have 2 valid replicas, but master believes there are 3. GFS is designed for eventual consistency, that is, over time system notices inconsistency and fixes them, bringing everything back to the required state. So while temporary inconsistency exists into the system, but system always moves forward towards the consistent state again. So we saw that it is possible there can be some inconsistency into the system, right? The question is, how does system detects those inconsistency and recover itself, right? So this is done via heartbeats to the master server. That is, every chunk server sends a heartbeat to the master server, signaling that, hey, I'm alive and here's what all chunks that I have, right? Master server would check into its metadata that whether is there any chunk that should be present into that particular chunk server but is not written into the heartbeat, right? Might be possible because the data got lost on the chunk server, right? If it detects any of such inconsistency, master server quickly tries to identify what next particular chunk server should get the replica of that particular data, right? This self-healing process ensures that even if failures occur, and they do often, right, the system stays reliable and data remains accessible. So next thing is checksum and data integrity. So replication and recovery keep data available, but what if the data itself silently fails or gets corrupted, right? This is where the checksum comes in. Think of it like a librarian stamping every page of the book with a seal, and later when someone asks for that particular book, librarian checking whether the seal is intact, right? That ensures that the pages haven't been damaged or altered, right? In Google file system, whenever a client writes data, chunk server splits that particular chunk into smaller blocks. There are 64 KB blocks, right? And for each block, it computes the checksum and stores it on the disk alongside the data in a separate checksum file, right? Later, when client reads the data, chunk server recalculates the checksum using the same hash algorithm, right? And checks this particular checksum with the stored checksum. If there's a match, it can be ensured that data is not corrupted and chunk server can return the data back to the client. But if there's a mismatch, it means there is a corruption on that particular chunk, and client reports this particular corruption to the master, so that master can arrange for a new replica for that particular chunk, and to the client, chunk server responds to fetch this particular chunk from any other replica, right? So behind the scenes, Google file system is constantly validating data integrity, ensuring that what you read is always accurate and not just available. Right. So far we have covered the chunk servers part, how they replicate, read, write and recover. But who keeps track of all the shelves, books and copies? That's the master node, the brain behind Google file system or GFS. It manages namespace, decides which server is primary, collects heartbeats and much more. In the next part, we'll dive into the master's role, its internal architecture and how it avoids being a bottleneck. Okay, to recap this part, we covered replication that ensures multiple copies across servers, read path that helps client directly fetch from any of the chunk server, write path and atomic appends that guarantee consistent updates. Next is consistency and recovery that keeps system self-healing, and last is the checksum that protects data integrity by detecting corruption at the chunk level. Together, these features helps system being highly fault tolerant, reliable and accurate. In next part, we'll open up the brain of the system, that is the master server, and explore how it manages everything behind the scenes. So please do like, share and subscribe to my channel. If you have any feedback or want to cover any new topic, please do add them into the comment section. And thank you so much.